Okay, thank you. And thank you, the organizers, for organizing this meeting and for giving me the opportunity to speak in it. So let me just start with this slide, which shows here a very cute animal. So snakes look very, very nice animals, but they can be also dangerous because they can produce large amount of venoms, but also more large amount of venoms, larger amount of venoms. And when an fatal encounter occurs in the wild, the snake, if threatened, if cornered, will react by biting in a defense manner to the other animal that is disturbing it. So we need antivenoms. The antivenoms that we have in the market are being criticized because of the low effectivity they have against for treating many snake bites. And this is true. The therapeutic antibodies per vial in most of the antivenoms that are in the market, these are particularly for the African market, is low, is between 5 and 10% of the total antibodies are clinically useful. And in the case of antibodies against the other group of species, Elapidae, the situation is similar. The protein also is quite different between products and products, from 5 point something to 120 milligrams per ml. And the potency against the viperids and the elapids varies also a lot, between 1.7 to 33 milligrams of venom per milliliter to, in the case of viperids, to 0.3 to 1.8 for elapids per ml. So this means that depending on the load of venom that is deployed in the venom patient, you will need a lot of milliliters. This means a lot of vials, and if you put here in grams, can be up to 220 grams or even less, about 10 liters of antivenom for a whole load in an envenomation. So this is the drawback that we experience, that we have with the current antivenoms. So it has been suggested that oligoclonal mixture of human antibodies can be alternative to the current antivenoms. But for the moment, the only that has been shown is 2 cases. This is one, the initial one in 2018. And if you make some calculations of the potency of this oligoclonal against the dendrotoxin from Dendroaspis polylepis, the potency is 27.7 milligram of venoms neutralized by gram of monoclonal. So it's not much difference between the potency that we observe in some of the currently old-fashioned antivenoms. And the same happens from this that we heard also this morning against this other, against Nadia Caucia, where if you make here some calculation, the potency is also about 24.7 milligrams per gram. So it's also a low potency for something that should be like the next generation. I think it's more for the next generations, the next generation solution. Why is this so? This is so because monoclonals are technology-driven antivenoms, antibodies that are single epitope binders, which are selected by panning of naive antibodies. And naive antibodies are selected by, well, here it should come here something that says affinity. It's here, but it's not seen in this slide. So what the selection of the antibodies is based on affinity. And there is no scientific rule that says that affinity has anything to do with neutralization. It could be, but it could not be. So affinity is, in my view, not the best selective criteria that you need for selecting better neutralization antibodies. On the other hand, these old-fashioned conventional polyclonal antivenoms are actually an array of monoclonal antibodies. Every single antibody is a monoclonal antibody because it's the way it is synthesized by a clone. Here what we have is that each of these monoclonal in the polyclonal antibody can bind to a different, related but different epitope, and this gives you two advantages. One, covers more surface on the molecule. Second, it can be more paraspecific than the single binder to an epitope. This is what happened, what I summarize here. So you have a single binder to a single epitope. This could be this. It is shared between different molecules that are different in other parts of their structure, but they share an epitope. But here you have many different ways of recognizing different different toxin. So this means that the paraspecificity of this type of molecules here is restricted, whereas the other can be much more larger and can become even pan-specific of a certain group of venoms. So with this in mind, we set up in November 2020 and through May 22 that finished this proof of concept, the COVID time where you could not go out for beer, and the option was working in the lab or staying at home, and we prefer to go to the lab. Actually, you see here, this is the whole crew of the lab. We are now 1, 2, 3, 4, 5, 6. So this was a lower size, but I amplified so that you see also the persons, not under the name of the institute. And this work was done in the lab here at the Institute of Biomedicina de Valencia by those people, and with funding from the Global Snakebite Initiative and in collaboration with East African Venom Supplies, where we get most of the venoms also. So the proof of concept is that current antivenoms can be refurbished to clinically effective products. So if just a comment to the characteristic of an antivenom, because this is important to understand the concept. Look at this antibody here. 1 gram of IgG, 150 kilodaltons molecular mass, 150,000 grams per mole, means that you have 13.2 micromoles of antigen binding sites. So this is the limit for the stoichiometry binding of an IgG molecule. Is this monoclonal or polyclonal? Nobody can distinguish. It's the same. The characteristics are absolutely the same, whether it is produced in, it's only a question of the formulation and the production. For a Fab fragment, if you do the same calculation, you have 18.2 micromoles of antigen binding site per molecule. This means that the maximal binding capacity of an IgG for a three-finger toxin, 6.8 kilodalton, is 123.8 milligrams per gram. For a PLA2 molecule, you can capture up to 247.6 milligram per gram of antibody, and for a dendrotoxin, you can capture or bind about 111.6 milligrams per gram. So this is important to bear in mind. But there is also a trick. This is binding to toxins, not to venoms. So if you have a venom that contains 15% of a three-finger toxin, and you bind, and by binding this toxin, you abrogate the lethal activity of the hull of the venom. So you can increase the maximal binding capacity against this alpha neurotoxin to reach 825.3 milligrams of venom neutralized by gram of antivenom, because you have a single epitope that need to neutralize, which is 15%. So the amount of venom that you neutralize is the same quantity that we saw stoichiometrically, but divided by the relative abundance of the toxin. And the same happened in this case. So this is actually the numbers that set the upper limits of the neutralization of antibodies, not the stoichiometric binding or their affinity. So in this case, how can I take this away? Well, this was the formula for the maximum binding capacity, which takes into account the relative abundance of the toxin in the venom. So these are the essentials of antibodies that could be used for neutralization of toxins or venoms. So with this in mind, we started to profile all the venoms from African Naya species, and this all with asterisk is the one that entered in the study. We determined by toxicovenomic analysis of the venoms a toxicity score to catch those molecules that need to be neutralized to neutralize the venom itself, and determine here a toxicity score that takes into account the LD50 of the toxin, but also the relative abundance in the venom. And everything that has a toxicity score above this threshold is potential life-threatening toxin and should be neutralized in good antivenom. You see here that sometimes the most abundance have also the most relevant toxicity score, but other times you have lower abundance molecules that are the ones that drive the lethality of the venom. So then we started to purify in a large scale method the toxicovenomics inform medically relevant toxins. You see here, and here is the mass spectrometry to identify these toxins, and the same happened here, so that you can work with hundreds of milligrams of venom in a single chromatographic run and isolate decent amounts of toxins. And with these toxins, we put in columns and make affinity columns to isolate their binders, which are the antibodies in antivenoms. And for this, we used outdated commercial antivenoms that we had in the lab, in the fridge, and we had about 60 grams of antivenoms, and we started to isolate from each one in a serial manner the antibodies that bind to these affinity columns. You see here, these enter these columns, what it was not bind were to the other column, retain this, what was not bind to these columns again to the third one, and so on. And so we collected and immunodepleted the outdated antivenoms from the relevant antibodies, toxin-specific antibodies. And so then we tested the capacity, the neutralization capacity of these pools of toxin class antibodies individually or in combinations with themselves. And you see here, per instance, how dramatically increase this neutralization of 52 milligrams per gram to up to 800 when you make the right combination of antibodies. And the same happened to most of the other classes. In some cases, with one was enough. In some other cases, it was even not effective, and you needed to put one or two to have the maximal effect. So this is summarized here, where all the taxa in Naya, clade, and also taking into account hemachatus, had a good potency that in principle allows to neutralize the venom that they are able to inject in a single bite. So this is, as I mentioned, very sensitive information that one needs to have at hand. How much can a snake inject to a victim? Taking into account that it is not the amount of venom that you can force the snake to bite into a jar, because this is the maximal amount. But any bite of a snake is a defensive one. So it will take as quick as possible to give the snake a window of opportunity to fly from you and avoid the danger that you can inflict the snake more than it can inflict you. So it should be rapid, and therefore, just by the physics of releasing a fluid through a small hole cannot be the whole load that is in the venom gland. So in the farm in Kenya, people have determined some of these parameters by letting the snakes bite by themselves without forcing, and this gives a better idea than just the full extraction. And then we collected also data from the literature, but this data in some of them is not clear if they are wet venom or if they are dry or if they were forced to be or not. So these are very still needs a refinement to have this parameter as more accurate. Nevertheless, we estimated a venom yield. For this venom yield that we estimated, we calculated also the amount of toxins, antibodies that need to be in a single vial to be a single therapeutic dose per vial. And we came out with something like 6.2 to 12.8 grams would be for the whole venom load that can be deployed in a victim, a single therapeutic dose that will cover each and every one of these species. And we prepare then a 55 milligrams per ml doses that used against 5 LD50s of each of these taxa, and calculate the potency and the grams of antivenom that would be needed for a mean venom yield. And you see that for most of the species, except for some that need more, is around 1 or less than 1 gram for the mean average venom yield. There are some that you need 2.4, 2.7, and this taxa they need 4.8. But well, this is an estimate that it is in concordance with the previous analysis, but a little bit lower gives you more hope that to have a single dose in a single therapeutic dose in a vial or in a couple of vials. So to test the hypothesis that this is correct, then we set up in vivo experiments where we sought to neutralize 5 LD50s of each of these taxa with a fixed amount that was calculated according to the previous data. And it was 13.8 milligrams of antivenom per mouse except for this Naya that was 18.1. And you see that except for one death, all the animals survive. So actually, think we are in the right track with these calculations. The same happened for Polylepis. You have here the potency that we obtained for each of the 5 species of subspecies of mambas. This is the venom yield estimated. And this is also the statistics and the needs. And here you see this is round, 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 and this is 0, because this round that come up here are also 0. So are less than 1 gram from the same vial that we tested with the Naya. So the vial includes also paraspecificity against each and all the mambas. So this is for the moment where we are. Of course, the goal in the next future is to have larger scale, larger purification of antibodies to formulate a better and more potent mix of pan, Naya, and Dendroaspis antivenom formulation and test it in vivo, and eventually to manufacture between 500 and 1,000 vials for conducting clinical trials. This was also the dream of Royan Taylor, who you see here very smiling because it was at the launch of the roadmap in Geneva. And sadly, a few weeks later, he unexpectedly passed away. And so there's this work, this presentation, and the next work is also dedicated to his memory. And with this, I think this is what I had to say. And I left the rest of the presentation, if there is time, just for questions. Thank you.
Thank you, Juan. I'm sure there'll be questions.
So thank you for a nice presentation. And I'm also glad that we see this the same way. One antibody can bind to one toxin, and that's what we're after.
Yes, well, to 2.
Yeah, 2, if it's an IDT. Yeah. So this would, just a clarification with this with affinity and neutralization. Of course, apologize if that wasn't clear, that is not only affinity, it has to be neutralizing. That's step number 1. But then if we have a higher affinity, as you point out yourself, you can have 1 antibody per 1 toxin. You show the data here, but that is the ideal case. You could have less antibodies, but it's if you have a low affinity antibody that doesn't bind to your toxin, then it will not make any sense.
But every antibody binds to the antigen. We isolate it by binding.
Yeah, you do an affinity.
So this means that in this case, if this were true, we will have a stoichiometric binding, and we will have the maximal neutralization, and this is not the case, simply because there is also a dynamic of binding and releasing, and this enough. You need enough affinity to capture the antivenom, or to get a stable binding in a complex environment like a body.
Yeah.
But if you have more, if it binds to a toxin without neutralizing it, if you increase the affinity, it will bind to the same toxin without having any neutralizing activity. So because you are only increasing the binding to the same epitope.
Yeah, we're not after the non-neutralizing antibodies, none of us. It's just a high affinity is still a good thing. It's never a bad thing with a high affinity.
Is a good thing. If there is enough, more can be worse.
Yeah, it's the law of mass action. It's nothing special. Concentration of toxin, concentration of antibody. Thank you.
It's just to follow that on. Can you set the phage display to look for affinity and neutralization at the same time? Is that feasible?
And you can direct the phage display to actually go for the active sites of an toxin, if that is.
If you know where the size is, and
if you know where it is.
you can reproduce it in a conformationally
Yeah,
similar conformation.
So you can enrich
conformation
for
similar.
antibodies
Yeah.
towards the active site.
Sure.
You can also do it in cycles. Yes, that's possible.
Hey, Juan, great talk. It was just a point on the affinity versus neutralization. I mean, the way we are doing it with phage display is that we first select for high affinity, and then from the high affinity binders, we select for neutralization. So we're not saying that high affinity is neutralization. We are also, like you also select from a high affinity bunch, and then you select the neutralizers from there.
But the neutralization that you select is the one that you published. These are the monoclonals that you selected. And this is the neutralization activity that can be calculated from these studies. So it was not something great. As a starting point is okay. But in my view, and this is why I put this title, this should become in a later stage.
Yeah,
this should become in a later stage. Of course, I wish if I click my fingers and all these antibodies were humanized, it would be perfect, much better than it is in this study. But it's something needs to go step by step and not first trying to do things that are not in a solid ground.
Yeah, I agree. But that actually brings me on to my actual question. For the maximum binding something calculations, can you maybe go on to that slide? The
Which
one where you
one?
have the 40% and the 33% of the venom? Because I didn't really get how you calculated.
How?
How you calculated that
Okay.
all of a sudden 1 gram of antibody is binding more than 2 toxins. I might have misunderstood something.
I may. Where is the? Because
It's
also
disappeared.
it's not facing me. Now I have it here. Let's go here. Oh, this is not. No. So here, for instance,
It
You-
was okay. We can also start here.
You have here the maximum. The maximal effect was 1 to 4 in mole terms. This means that you have 7, according to this data, 7.8 grams per mole of free finger toxin, 1 and 4 times 150 grams per mole of IgG. This means the calculation is 76.9 micrograms of IgG per microgram of alpha cobratoxin. This is just first grade mathematics. This means you have 13 grams of alpha cobratoxin per gram of monoclonal antibody. You convert this to a gram and you put here 13 milligrams. The 13 milligrams are 37 milligrams of Naja cautia venom, because this is 35% of the total venom. And this 37 milligrams of Naja cautia venom that are neutralized by the anti-venom is a you have a potency, because these are 2 LD50s of ED50 divided by N divided by N minus 1. N is 2 divided by divided is 1.5. So this means that you have 27.7 milligrams that can be neutralized in this case per gram of antivenom.
Yeah, it was not a.
There is no other way to calculate this.
It was actually not this that I was asking about. It was the one where you calculated.
The previous.
No, go a bit further. Also, I think you have
This is
You-
exactly the
No,
same.
no, go a bit,
calculation.
go further. Go 1 or 2 slides further. The one where you have a circle diagram with like 13% in it, where you calculate that you can bind more.
Yeah,
That was what I didn't really follow. This
this,
thing, 15%.
well, if you need 15% epitopes to neutralize the whole, the quantity of venom that has this 15%, this means that you are multiplying the total amount of venom that you can capture by dividing the maximal capacity by 0.15.
But you still only inject the same amount of antibody, right? Each antibody can't, we agree each antibody can't bind more than 2 toxins.
Each antibody will bind 1 or 2.
Yes,
But the amount of antigen that you bind stoichiometrically is the same as here. But the venom that you take out of the solution by binding to this amount of toxin is much higher if the abundance of the toxin that you bind is less.
yeah, I think I've hogged this microphone for long enough. I can see young Glenn.
I think this is a discussion best sorted out by
It's a
at the
discussion
bar
that-
tonight
that
over a whiskey.
The best way to settle the discussion is take a piece of paper, do your calculations, and try if they fit or you find another way of another
So-
solution.
So Juan, just
Yeah.
go back to that other slide,
Which one?
the one you just had up with the pie chart.
With the pie chart.
Yep.
No. Yeah. Here.
Right. So tell me if I've got this right. So what you're saying is if the toxicity score means that only that fraction that's 15% is
No.
greater than 1, in other words, that's the only fraction that's likely to kill your patient, correct?
This is just an example.
Yeah,
not a
but
real
this is
one,
what I think you're
just to
trying to
illustrate
explain, isn't it?
the concept.
So then you're saying if that 15% was equal to 123.8 milligrams, if you provide the antibodies to neutralize that, you don't have to worry about neutralizing the rest of the venom because it didn't have a toxicity score that was going to kill your patient anyway.
Yeah,
And that means that 15% or 123.8 milligrams is 15% of a total of 825.3 milligrams of whole venom.
yes. Well,
Okay.
is 50 is this the
I'm not saying I'll get-
multiply by 15%?
You've done your first grade maths.
So I if I pick one, I take all of it. You are all each different molecules. If I take you and you are attached to everyone else, then I take the full ball. If that venom needs to pick up 2 to neutralize, I need 1 for you and 1 for them. In each time I take all the balls, but taken together, I get 2 times more anti-venom for neutralizing the whole of you than in the first example. So this is the concept.
One final question up here.
Because once you neutralize something, you neutralize milligrams of venom. So you can't take milligrams of venom. So you are really neutralizing the milligrams of toxin. And the rest come together.
Hi, Juan. Stuart Ainsworth from Liverpool School of Tropical Medicine. Maybe changing tact a bit on what's been discussed, but your final antivenom, it's a refined product towards certain toxins, yeah? The most important toxins. Well, yeah, the medically important ones. One of the citations of, you know, one of the main problems with antivenom is the cost of its manufacture. Now, the way you're manufacturing your antivenom here is you need to have a lot of venom, which is expensive. You need to purify out the most medically relevant toxins, which is expensive. You have to do it multiple times. You then have to go through multiple chromatography steps to get the antibodies afterwards. So I'm just wondering, what is the financial cost do you think this is going to be? Is it going to be cost competitive? So it's an economics of scale.
All of this was done with $300,000, not with 3 million. So this is the problem is not the code. And on the other hand, if you end up with a product that is very effective, the market that you open is more huge than now. And there is no single manufacturer that can cope with the production of all what we need. So there is market for, and they adjust the unique to the production in the manufacturing setting is minimal. It's just to add things in between. Regulatory, this could be an issue, etc. But what you need to adjust is much simple than to change the whole mind and start producing high technological molecules. So
Right.
at the end, if you want to save life, it will cost money, but it's a money that needs less investment in this way than by high technology. This will come by taking a better starting point and start to put technology on it and humanization and whatever. It will come, but we need to solve the problem now before taking the next step.
It will come, but our next speaker won't if we don't
Yeah.
stop soon. So I think we'll have to call it quits there. Thank you, Juan, for a great talk. I think lots of discussions for the bar this evening.